Okay, hi everyone. I'll go ahead and get started. So it's great to have you all here this afternoon. So I'm Tiffany Morris. I represent Illumina. I work in market development for precision health screening, focused mostly on preventative genomics and pharmacogenomics, and really trying to implement that into clinical healthcare. So today I'm here to share some of the latest advances with Illumina whole genome sequencing. So I'd like to start by sharing some improvements we've made to the coverage and accuracy driven by our DRAGON platform, which is Illumina's analysis platform. And then I'll introduce Illumina Complete Long Reads. So to start, DRAGON is the hardware behind Illumina's analysis platform. And it's really driven by three technologies. So first, Graph Genome aligns many different references in the particular population that you're studying to capture the variation and to help drive improvements and resolve complexity. So this is particularly useful in complex regions such as the MHC region. Additionally, we utilize machine learning to improve precision. And then as we gain more and more truth sets with both short genome sequencing and long-read genome sequencing, we can feed that back in and develop targeted callers. And because of my focus on pharmacogenomics, I can call out a particular targeted caller here, CYP2D6, which is a particularly challenging gene for pharmacogenomics. But it's also very important as CYP2D6 is responsible for the metabolism of up to 25% of drugs. So being able to use a targeted caller to better understand these complex genes really helps us understand the genome in more detail. So last year, we participated in the Precision FDA Challenge with our 4.0 version of DRAGON, which was our update last year. And in this challenge, the DRAGON software combined with our NovaSeq platform received the most accurate human genome variant score, which was 99.83%. So we showed to be the most powerful and accurate secondary analysis tool amongst the other products that were involved in the challenge. And in that version last year of 4.0 was when we first introduced the CYP2D6 caller that I mentioned. And in this year's update, 4.2, we have further improved that CYP2D6 caller for pharmacogenomics. In addition, we've improved carrier screening insights with targeted callers for CYP2-1A2 and HbA. And we've also expanded cardiovascular and blood typing insights with additional targeted callers. So we're continuously driving accuracy, precision, and broader coverage of our short-read genomes with improvements to our DRAGON analysis platform. And as DRAGON short-read whole genome sequencing improvements in DRAGON address many known challenging variants, in parallel, we're also improving our coverage of the genome with our new long-read technology that it aims to address the much more complex regions, the small percent of complex regions still remaining in the genome. So now I'll move on to talk about the Illumina Complete Long Reads. So this is a fundamental technology on which we plan to build a number of products. So initially, our first product was launched earlier this year, which is the human whole genome long read whole genome. And later this year, next month, we'll be launching the human targeted enrichment. And so thinking about the targeted enrichment product, the idea is to focus on regions of interest and that you find particularly challenging that you want to customize and focus a long-read technology on. So you would run a short-read genome and then enrich particular regions with long reads. And both technologies are currently available on the NovaSeq 6000 and NovaSeq X series, but the idea is this technology will be species and platform agnostic. It's just these initial products that are focused on human and on our NovaSeq platforms. And then, as I've mentioned, our Dragon analysis platforms before, that will also be available with long-read technology. And currently, it's in cloud-based, but we have a roadmap for making it a local analysis as well. So just to talk about some of the capabilities, so it's highly accurate. As I mentioned, we received high score for the short-read genome along with Dragon and NovaSeq at the Precision FDA Challenge, and that score even improved a little bit more from 99.83 to 99.87 with the long read. So we're really pushing the accuracy and the boundaries there. And then it's a really simple workflow, really low DNA input. And I can talk a little bit more about that. So it allows us to sequence up to 3,000 highly accurate whole genomes per year. And if you're using the enrichment, that can even be more, since you're just focusing the long read on certain targeted regions. And this is really 25 times more than other long read platforms. The N50 score, which is a measure of read length, shows that the average read lengths are between 6 to 7 kb, and some of our early access customers have seen up to 20 and 30 kb generated. And then the 50 nanogram input requirement is actually 90% less than other current long read technologies. So this is really enabling early access customers that have found this low input really valuable due to, samples that you just don't have as much available for. So now I'll give a brief overview of how the technology actually works. So this utilizes many common Illumina methods. So we start with a tagmentation step to normalize the long fragments, those that are greater than 10 kb, down to sizes between 10 and 15 kb. And then we do what we call landmarking, which is a molecular marking that introduces base modifications at single base level. So each molecule in the tube will actually have a unique mark or a fingerprint that will map it back to the original molecule. So then once the landmarking is done, this amplification step with fluorophores is done to get enough signal. And then we we amplify those fragments in another tagmentation and sequence. And the magic is really in the data analysis, where those sequenced pieces are then combined with the short read genome to reconstruct the original molecule. And so this is a novel and unique technology, and we're really, really excited about some of the data we're seeing. So I'd like to talk a bit about the workflow. So this is an extremely easy workflow. The sample extraction is just straightforward. It doesn't require any specialized extraction, no shearing, no size selection. And then the library preparation is also very simple. Again, low input, as low as 50 nanograms, and it only requires standard NGS lab equipment, and it's highly scalable and automation friendly. And as mentioned before, it's currently compatible with our NovaSeq 6000 and X series, with plans to expand products in the future to other platforms. And at the moment, it's available with our Dragon analysis software, cloud-based. So to dive a little bit deeper into some of the proof points I've mentioned, we'll start by talking about the quality of the DNA. So this plot on the left shows we've mimicked degraded DNA using covariance shearing. So on the left side, you can see a 1-second shear, and then a 3-second shear, and then control. And the top part of the plot is an N50 score average, so 6 to 7 kb read lengths, and the lower is those up to 200,000. And you can see the robust data across the 3 samples. And then in the middle, we're looking at the DNA input flexibility. So here, the plot shows from 5 nanogram input up to 1,200 nanogram input. Again, the top plot is looking at the 6 to 7 kb lengths, and the second plot is looking at the longer, up to 200 kb lengths. And again, you can see the robust data against the different input sizes, input amounts. And then in the third plot, we're really looking at DNA purity. So comparing samples that have common contaminants, and also comparing blood and saliva samples. And again, you can see robust data across the three. So now, just to dive into some actual data for a moment. So this first gene that I'll mention is STRC, which is related to deafness, and it is a complex gene. And here we have an IGV plot showing 22 kb window. The top part of the plot is Illumina short reads, and as you can see, there's some challenges with the mapping there, some large gaps. I can probably show those here. And in the middle, then we see Illumina complete long reads, and then on the bottom is the on-market long reads. And you can see that Illumina complete long reads really resolves those gaps. So then here is another medically relevant gene in CF1 that again has a lot of challenging areas along the gene. And you can then again see that Illumina complete long reads is comparable to other long read technologies in fulfilling the gaps. And I won't go into too much detail with these next 3 slides, but I just wanted to mention that it can also resolve complex structural variants and detect medium-sized deletions and also large indels. So also I'd like to talk a little bit about phasing and take a little bit of a closer look at human HLA genes. So the MHC genes are on chromosome 6, and this is a really highly polymorphic and challenging region to sequence and map. And so here, actually, I had mentioned earlier in the talk that our Dragon software has specific HLA caller, so it actually does a really great job resolving HLA. But there's still a challenging area here, highlighted in yellow, where it's difficult to discern different haplotypes. And so if you use Illumina complete long reads, you can really then clearly identify the different alleles, and then it's very easy to differentiate the two with phasing. So then now I'd like to switch and dive a little bit deeper into the long read product that we have coming later this year, the long read enrichment product we have coming later this year. So this is our targeted long read. So this is a short read whole genome of 30x, and then you choose the areas that you want to enrich for long read. And again, we'll look at a medically challenging gene, GBA, and here we've highlighted 2 regions that have been challenging to map using short read. And here in the middle is Illumina complete long reads whole genome, and then at the bottom you can see Illumina complete long reads with enrichment, where you've just focused in on those challenging areas and been able to resolve them quite clearly. And I'll mention again, so HLA-A, so you can do this with enrichment, where instead of doing the whole genome with long reads, you just focus in on that region and you're able to resolve those haplotypes very clearly. The same with HLA-B and HLA-C, and you can do the similar target enrichment long read for other similar challenging regions. So we've had a number of early access customers really happy with using Illumina complete long reads, and I wanted to highlight this particular story from Michael Quayle at the Sanger Institute, and I'm highlighting this one in particular because he looked at CYP2D6, which is a gene for pharmacogenomics that I've mentioned a few times, and it's again a good candidate for long reads. There's a number of star alleles or haplotypes that are still difficult to resolve even with our short read genome caller, and so long reads can help further look at those more difficult rare star alleles. So Michael Quayle has said, we're excited about Illumina complete long reads. The library prep was straightforward with flexible input requirements. We are impressed with the accuracy of the data along with the read links and phase blocks that can be generated on Illumina sequencers. So just to summarize, we've really developed this technology to be as accessible as possible, to be robust and flexible, to allow really low input and an easy workflow, and to make it as easy as possible to combine this with the short-read genome to really look into these more complex regions of the genome in more detail. And there's a number of us here from Illumina today. We're happy to talk about short reads, long reads, Dragon, or any number of our other informatics updates and genomics updates that we're working on at Illumina. So please feel free to come find us, and if anybody has any questions now, I'm be happy to try to answer them. Thank you. Yes, go ahead. Oh, she's got a microphone.
Thank you. Sorry, I did not know if I may have a question now or later, so I was perplexed.
Go ahead.
So thank you so much. Very interesting the approach that you are proposing for, whole genome 30, coverage 30, and the targeted sequencing.
Yes.
My question is, so these may, this targeted enrichment may affect coverage of the standard whole genome sequence regions in terms of short reads?
No.
First question.
Okay.
Second, so which are the possible use of this approach compared, for example, to the classical gene panel approach? So which is the added value you may see in using this targeted enrichment whole genome sequencing compared to panel? Thank you very much.
So to answer your first question, you're doing a complete 30x whole genome. And so adding the targeted enrichment on top of that won't affect your 30x whole genome. You're basically getting a traditional 30x whole genome with the additional enrichment of the regions that you choose. And so with a targeted panel, you'd really be focusing in only on those regions, but with this, you're getting the whole genome with short read, and then you're diving deeper into those regions you've highlighted to have long read sequencing there. So those are the regions that are particularly challenging. So you'll still have whole genome coverage, and then you'll have that additional long read coverage of those particular areas. Does that answer your question? Structural variants, indels, deletions, pseudogenes, anything.
Copy number, right? Structural copy number, whatever that might be, much more accurate in picking up them.
Exactly.
Thank you so much.
Yeah.
I have a question as well. So the presentation was mainly about mapping, but what about the de novo assemblies? For example, was it benchmarked on prokaryotic novel bacteria like de novo assemblies or not?
That's not a question I can answer. I can find that out for you, but I'm not sure if we've done any work on that.
Okay, thank you.
Okay, great. All right, thank you.
Thank you.